Welcome everyone to today's video. Uh, we are done with the topic of circular motion, which we covered until the last one, and we did a lot of questions and we finished up with the topic, and we are ready to start a new chapter called work energy and power. So, as the name suggests, work energy, it deals with the topics of work done on a body. What is work done by a force? So today we'll be defining what is work done and how do we think about it in a natural way. And then we'll think about what is energy in further topics of this chapter, that what is energy, what is kinetic energy, specifically what is potential energy, what is the relation between kinetic and potential energy. Then we come up to ideas which you would be already knowing, that is conservation of energy. So you'd be knowing something like the sum of kinetic energy and potential energy, it remains constant in some situations. So how does that come to be? Then we'll be discussing a new idea which is derived from the idea of conservation of energy only, that is work energy theorem. Then we'll be moving on to the idea of conservation of momentum, in which we will see the cases of collision of two balls in different ways, and how do we calculate velocities in those cases. So this is a very exciting chapter. So let us start with an example, that how do we think about work done. So when we think about work done by a force, we think about some force is acting on some body, and that body is either getting displaced. So for example, I'd be taking a block, there is a block lying on the floor, or there is a book lying on a table, or a pen lying on a table. So I posed my pen on the table, so the pen got displaced due to the force applied by me. So that means I have done some work on the pen, or I have done some work on the book which was kept on the table. So we have to think about what are the forces acting in those cases, and what forces are doing the work. Should I say gravity is doing work on the book which is being displaced? The book is lying on a seemingly horizontal table and I displaced it. So would I say the gravity or any other force like normal force is doing the work on the book? And how should I think about the work done in those cases? So one case can be this. Next case can be, let's say, if we are trying to change the shape of a body. For example, I am taking a rubber ball and I compress that rubber ball by the forces applied by my hand. Or I can say you might have seen some YouTube videos in which they take a ball and they put the ball in the ultimate strength testing machine, in which they compress the ball. So they are trying to compress the ball. So in that case we are trying to change the shape of the ball. So what forces are doing the work on the ball? What are the forces done by the particles, the forces by the particles which they exert on each other? And when we talk about particles, do we think about particles in our air too? Are they also doing work on each other? They are exerting force on each other, right? Some attractive force or some kind of repulsive force. So how do we calculate the work done in those cases? So all that comes with the idea of work done. So how do we define work done? The work done by a force. We define the work done by a force by taking the dot product of the force vector and the displacement vector. So we say the work done by a force is equal to the dot product of the force vector, the work done by a force is defined as the dot product of the force vector and the displacement of the particle or body. So that is the definition for work done. Work done is defined as the dot product of the force vector and the displacement vector. So this is what we have to learn actually. That how do we write this, and what is the physical implication of this definition. So we say, let me represent work done by some variable W. So W represents work done by a force, and this is equal to the dot product of the force vector and the displacement vector, F dot delta R, where F is the force acting on the body and delta R is the displacement of the particle or body. So next we can think about some other aspects of the definition of work also, that work done being the dot product of force and displacement is also, we can talk about the units of work. So the unit of work is Newton meter, since we have evaluated the work done on a body by multiplying the force of the body and the displacement of the body. So by multiplying Newton and meters, we must get Newton meter. So the unit of work, or SI unit of work done by a force is 1 Newton meter, which is written as 1 joule or 1 capital G. So again, going back to the definition of work done, that what is work, we can say, let's say the angle between, and this is the idea which we are trying to see, that let us take an angle theta. So if the angle between the force vector and displacement vector is theta, then we know that in dot product a cos theta component comes. So the work done by a force is simply F delta R and the cos theta component, right? Because dot product yields a cos theta value, where theta is the angle between force vector and displacement vector of the particle or the body. So this is also a useful definition of the work done. So this also reminds us of the idea that despite the work done being a product of two vector quantities, that is force and displacements, it is a dot product. So since it's a dot product, work done comes out to be a scalar quantity. So next we'll try to make this physical sense of the expression which we have just done. That we have learned that okay, work done is equal to dot product of force and displacement. That's what I've been talking about for the last 5 minutes. Now how does it make sense to us? So let us take an example, and from that example we'll be trying to make sense of this expression. So let us take a case of a block which is lying on a floor. Let us take a block. So this is the block which we are talking about, and some force is acting on this block F. Right. The magnitude of this force is F only, and the displacement of this block is like this. the block is getting pushed ahead on the surface, and this displacement is in horizontal direction, and let's say this displacement has a value on delta r. So the force is acting on the block in some slant direction, that is it is acting at some angle with respect to the horizontal. So it is acting at some angle, and the block on which it is acting is getting displaced, it is getting pushed ahead. So that means the block is being pushed ahead, like we trying to push a cart, a horse cart or any kind of cart we are pushing ahead or pulling ahead. So since we are pulling ahead, we are trying to pull it ahead by help of a rod or a string and so on. So since it's a pulling force, it is acting at some angle. So what does the definition of work done tells us here? So the definition of work tells us that when we are talking about the work done, then we take a dot product, that is f dr cos theta. So if I were to write f dr cos theta like this, f delta r cos theta, and I would just next going to rearrange the expression. We know this is the expression for work done, right? F delta r cos theta. Now I am trying to bring this cos theta next to the force term. So I can do this, that cos theta sits next to the force term and delta r remains as it is. So this means f cos theta into delta r. So this is just rearranging the terms, and we are trying to make sense of what is work done by a force. Okay, so now we know the angle between force and displacement. This angle is theta, and we know that when we take the dot product, so some expression comes, cos theta comes. So when we are taking components of force, so which component of force is in the direction of displacement? So you might have guessed it, this component is some f cos theta term, right? And the component which is perpendicular to displacement is f sin theta, because the component which is next to the angle theta is the cos theta component, and the component which is perpendicular which is in front of the theta angle is the sin theta component. So we would say that f cos theta component of this force F is doing the work, because the block is getting displaced in the direction of some particular force. So we would say the component of force which is in the direction of displacement is doing the work. It is responsible for displacement in the block. That means if f cos theta wouldn't have been there, in that way the force F would not have been doing any work, right? Let me repeat what I just said, that f cos theta is trying to displace the block in this direction where the block has gone. If f cos theta had not been there, if f cos theta had been absent, then no component of force would be helping this block getting displaced, right? That means no work would have been done by force F in that direction. So the only thing which is responsible for producing the work on this block is the component of force which is along the displacement of the block. And in the same vein, we can say that the component of force which is perpendicular to the block is not doing any work at all. It is not in this direction, so it is not contributing to the displacement of the block. So this is what the expression for work done tells us, that the component f cos theta is actually responsible for the displacement of the block in this direction. It is making the work done possible. So we will say that. So from this we can conclude that f cos theta is the one which is producing the work, which is making the block displaced in this direction. It is what is trying to make the block displaced in this direction. So that means that that component should come in the expression for work done. So it say the expression for work is component of force in the direction of displacement multiplied by the displacement of the body. So this is what we are trying to learn actually. We are not trying to learn the definition, not specifically trying to cram a definition that work done is F dot delta R. That is not our purpose, not even remotely. Our purpose is to understand what is work done, how work done happens. So work done happens when force has a component which is the direction of displacement. If there is no component, there cannot be any work done by that force, because that force is not interested in displacing that body in that direction. Only there is a component and the work done is only there only if there is a component, that is F cos theta, and in that case we say that component has to be multiplied by displacement, whatever displacement is there, and that comes as a work done. So we can say, how can I increase the work done of body? Now we can go a level further, right? How do I increase the work done? I can increase the force, I can increase the displacement of the body, or I can decrease the angle between force and displacement, which would cause more work done to happen. So now let us take a different example and try to look at this definition in a new way. So now let us take the case of a particle. Now in kinematics we throw a particle from some height and up to there, which is the topic known as projection of particle from some height or from some elevation. So let us take a case when a particle is thrown horizontally from some elevation. So the elevation of this particle above ground is some h, and it is thrown horizontally. So it strikes the particle like this with some velocity, and we know that because of gravity the speed of the particle is going to increase. One component is going to change and one component is not going to change, right? The velocity is one component will change and one component would not change. Which component would change? The component which is in direction of gravity. And which component won't change? The component of velocity which is perpendicular to gravity. So this gives us some hint, right? What we have been trying to see, that force tries to change or tries to do changes in the direction in which it is acting. So here gravitational force is acting vertically downward direction, right? So since it is acting in downward direction, all changes are going to happen in the downward direction. That is, the component of velocity in downward direction changes. Overall velocity of the particle increases, overall speed of the particle increases, but force cannot influence the direction in which it is not present. So let us try to draw the gravitational ng, gravitational force in the particle in vector terms, force vectors. So the gravitational force is always acting vertically downwards, that is towards the center of Earth. So we will be noticing that gravitational force is a constant, right? Again, force is a constant, and the displacement of particle, if I had to draw what is the displacement of particle, the particle gets displaced like this, delta r vector. It's not necessary that the delta r vector is parallel to the velocity vector, it's just like this delta r vector. So this is the displacement vector. I hope this is clear, that the displacement vector is something like this. Why I have drawn displacement vector like this? Because the particle's initial position is here, and irrespective of the path of the particle, the final position vector minus the initial position vector, that is the vector which starts from the initial position and ends at the final position of the particle, is the whole displacement vector. So this is the displacement vector, and I am going to calculate the work done by gravitational force on this particle which is being projected from some elevation. So now if I were to calculate the work done, I will be taking the definition. So this is where definition helps us. The definition gives us a starting point, and from that we have to build our understanding. Okay, this is the work done, this is the component which is going to be helping us, this is the component which is not helping us. So here the gravitational force in vertically downward direction. So the work done definition is F dot delta R or F dr cos theta. So now I am keeping the cos theta, the term cos theta with delta R. So I have to think about the component of delta r, that is the whole displacement of the particle, and its component in the direction of force. So like in the previous case, I was taking the component of force in the direction of displacement, right? Now we are doing the reverse. We are taking the component of displacement in the direction of force. So that is actually pretty easy to find. What is this delta r cos theta? Delta r cos theta. The force is vertically downwards and displacement vector is like this. This is the displacement vector and this is the force, direction of force vector. Not the force vector, direction of force vector. I hope this is visible to you guys. This is the direction of force, this is the displacement, that means this is the angle which we are searching for. So this angle is theta and this is the hypotenuse of the triangle, which is delta r. So what is delta r cos theta? So delta r cos theta, you might have guessed, this is the height, the side which is near to the theta angle is the cos theta side, and the side which is in front of theta is the sin theta side. So this is the cos theta side. So it say that this side is delta r cos theta, which is already coming up in our definition. So this is the, what is this h? This is the component of the displacement of the particle in the direction of the force acting on the particle. So we can write this as the force acting on the particle, that is F delta r cos theta, can be written as force on the acting on the particle into the displacement of the particle in the direction of force, or you can say component of displacement. Component of displacement of the particle in the direction of force, that gives us the work done acting on the particle. So with this we are finished with the definition of work done. So in all our cases which we have done up till now, we have taken force as a constant quantity. Force is constant, so we are directly multiplying force with the displacement and taking the dot product pretty easily. Now let us take the case when the displacement is very small, like a dx displacement or dr, change in position of the particle. So how do we define work done in those cases? So let's say the force acting on a particle at some instant is F. So that force I can write in two dimensions as some Fx I cap plus some Fy j cap. So this is a two-dimensional force, and I am trying to write the displacement of the particle. So on a graph, if I have to write the displacement of the particle is somewhere going like this. So how would I write the displacement of the particle in very small terms? I would say the particle is going in x direction, some dx displacement, and in y direction, some dy displacement. Now I cannot physically draw them because they are actually numerically infinitesimally small. Numerically small means that I cannot actually draw them like I have drawn them here. So I am only drawing a hypothetical look of how they would have been displaced for very small values. So these are the small values, that is dx and dy, dx in x direction, dy in y direction. So I would write some small dr vector, dr in during which scenario the force F of the particle acting on the particle can be considered a constant. So it would be dx in I cap direction and dy in j cap direction. So I would say some small work is being done on this particle by this force F in the small displacement. So the small work done can be written as F dot dr, it can be written as dw small work, and it's a scalar quantity. So I can write also this as F dr cos theta because of the dot product, or I can take the dot product of these two vectors, which would be easily able to take. So this value would come out to be some fx dx plus some f by deta. So this is a small work being done on this particle in the small displacement. Now let us take the specific case, which is the case which comes mostly. That force is some constant quantity and you have to calculate the work done. In the previous cases, what we have done, we knew the value of force, we knew displacement, and we didn't need to take some x and y components and so on. But what if this case comes? What our approach would have been in this case? So the approach would have been to write a component like this, that a small work done is equal to fx dx f by dy for cases when the value of forces is changing. So if the force is constant, then I can say force acting on the particle is uniform, F is uniform. Then I can say that I would be adding all values of work done acting on this body. So I'd be integrating them, that is dw. So it would be fx dx and f by dy. So when I put the integration sign, what does it means? It means that I am trying to add the values of all the small work done acting on the body. So x and y can be integrated separately, and that is the whole point which we are trying to come up to. That multiplying force vector and dot product is taking the dot product is pretty easy. But what if the force vectors has its components given separately to us? That is, fx is given separately and fy is given separately. What do we do in those cases? So when fx and fy are given separately, dx and dy are given separately, we take the dot product and then we integrate it. So we are integrating fx and dx, so definitely we would be giving some values that the particle is going from some x1 to x2, particle is going from some y1 to y2. So it is going from some x1 position to x2 and y1 to y2. So that is the whole idea, that we can separate the values of x1 and y1 given in a coordinate. In a coordinate, we are given the combined position of the particle and we are given that, okay, calculate the work done. But when we are integrating them, that gives us the ability to separate those coordinates and integrate them separately. So x1, x2, we are integrating the value of force from x1 to x2 and then from y1 to y2. So this would come out to be fx into, since fx is constant, we have already taken the simplest case. The fx is constant, it comes out of the integration, this becomes x2 minus x1. Since integration of dx is x only, so it becomes x2 minus x1, which I can write as delta x, and similarly I can write the other term as delta y. So this is the speciality for writing the work done like this, that whatever terms for x comes, a symmetrical term for y must also come. So this gives us fx delta x plus fy delta y as the complete work done acting on the particle in its complete motion. So this is how we define work done acting on a body. So in this lecture we will be covering up till this point only, since we have been covering a lot of theory. So we will be finishing this lecture up till this point. Our audience is also having the limited capability to absorb the information. So we'll be continuing with the next ideas in the next lecture. We will be starting off with some questions and we'll be discussing more in the next coming lecture. So thank you for joining and have a good day.